Okay, so this talk is going to happen in two parts. So the first part is really going to be about people. And we're going to look at some simple computational models of some simple learning phenomena. And we're going to try and get insight on how people are able to both learn from few examples, but also do experiments and know kind of what question should I ask in order to get the data that will help me learn. Then in the second part, we're going to try and scale up these ideas, particularly integrating them with LLMs and with program synthesis. So we'll start with people. And I want to start just by reflecting on what we want out of a system that learns from few examples. So remember, as Tom was telling us earlier, in our lifespan, we don't get an ocean of data. We often only get a few examples. So we want to build this kind of a picture where data goes into our system, our brain, or our machine, and now it's going to come some kind of hypothesis about how the world works, or what the underlying concept is, or what is controlling this regularity that I'm observing. And fundamentally, the reason why we want this is because we have some test data. We have some future life in which we're going to apply this hypothesis. And for now, we're going to try and aim for a system that is both efficient and flexible. And I'll explain what I mean by that in a second. But for the first part of this talk, I'm going to restrict myself to some really simple problems where there's not a lot of examples and everything is kind of low-dimensional and symbolic. And that's going to allow us to do an easier study. So by efficiency and flexibility, I mean the following things. One is we want to be sample efficient. We want to learn from a few examples. This means that maybe we need a good prior or inductive bias. Being flexible means, though, that we can learn infinitely many diverse concepts. And I'm going to try and do this by building a compositional program-like space of things you could learn. There's another notion of efficiency, which is that we want to learn with very little amounts of time or energy. And generically, this will be in tension with flexibility, because if we have a rich expressive hypothesis space, then it's going to be hard to search or optimize over those hypotheses. There's going to be a combinatorial explosion. Yet, if you look at the kind of stuff that humans can learn, we actually do a lot from relatively few examples and from relatively small amounts of energy. So I'll focus just on adult humans, who after we've been kind of pre-trained both by evolution and by development. But after that point, we can learn to use new mechanical devices like posture makers or bike pumps from just one or two examples. We can go to a new culture and learn how they greet each other from just one or two instances. And similar abilities seem to be really basic to human cognition because we see that even infants, maybe they couldn't learn to use a bike pump from one or two examples, but they can start to learn basic rules in language very, very quickly. So with this in mind, one kind of popular idea within both cognitive science and AI is to build something that is like a language of thought or like a programming language, a mental algebra for building concepts. And as long as my algebra is like a programming language, it can recursively compose things infinitely, I can get this massive, Turing-complete, radically expressive space of things I could learn. And that's really enticing, but there's a catch, which is that when you can think infinitely many thoughts, it becomes very difficult to know exactly what you should be learning. And one nice way of describing this is what is sometimes called the curse of a compositional mind. So what did Liz Spelke mean exactly by this curse of a compositional mind? So we're going to dissect this curse and understand why it's hard to fully deliver on this vision. So we're going to start with math or physics. And we're going to imagine what it would mean to learn something like this, which is very compositional. It's kind of like a program. And if you're really doing this compositional learning, it means that you're kind of playing Maxwell. Like you take the drawings of the fields, you think about like what kind of equation would fit this data, and you come up with this. And so this is tricky because there are infinitely many possible equations. Hardly any of them fit the data. And to make matters worse, infinitely many of them fit the data. So the curse is really two things. One is that most things don't work and infinitely many things work. And this is really the curse of compositionality. So what we're going to do is we're going to try to zoom in on some really simple learning phenomena with humans and understand how they address or could address this curse of compositionality. So remember, this is our picture. To make this concrete, we'll take an animal that we saw last time, the axolotl. There should be a picture of an axolotl there. I'm sorry it's not showing up. Ooh, the axolotl pictures all got destroyed. Okay, so there should be a picture of an axolotl. You could then hypothesize it means like a salamander with feathers. And we're going to try and do this learning in a kind of a Bayesian framework, which means that we're not going to conjecture a single hypothesis. We're going to try to represent our uncertainty. So remember, we have our invisible axolotl. It's going into the brain. And our brain is conjecturing various descriptions of what an axolotl might be. You're saying maybe they're salamanders or salamanders plus feathers. The plus is composition. They're probably not fish. Maybe they're kind of weird and pink things. And so we have this compositional space. It's infinite. And we're putting a distribution over all possible definitions of axolotl. So in order to do this in a Bayesian way, we're going to need a prior and a likelihood. But we also need this hypothesis space. And for now, we're just going to start with the idea that this space is language. And we're going to see how we can make that work. So the main thing that's hard about making language work as a representation is that inference is hard. So there's infinitely many things you could say. It's hard to know, given the data, what the right description is of the underlying concept. So to do this, we're going to have a kind of top-down and bottom-up process, where in the bottom-up process, there's going to be some imprecise, learned, data-driven pattern recognition engine that conjectures a variety of different hypotheses. And it's OK if a lot of these are wrong, because there's going to be a top-down process, which is going to reassess whether those actually fit the data, and also whether they're actually short, simple, a priori likely explanations. And so if something was kind of a bad proposal, it's going to be downweighed by this top-down process. So as you might be able to imagine, the bottom-up process, I'm going to use a transformer or a large language model. For the top-down process, we're going to use Bayes. And we get these two things to cooperate. To do that, we're going to draw a Bayesian network that defines a problem we're solving. So you can imagine something like this, where natural language is hidden, it's latent. It is somehow producing the data through this arrow. And so we have to define a prior over natural language. We have to say, what kinds of concepts might I expect to have to learn? And so we need a distribution over words, which we could use a language model. And interestingly, because these are autoregressive, we immediately become less likely the more words there are, which means that an LLM prior will give us a kind of Occam's razor bias towards shorter, simpler hypotheses. And you can also, because the neural network, train the prior to better fit human data. So this is our prior. And the proposal distribution is something that looks at the data and conjectures probable or plausible hypotheses. This something called an inference network or proposal distribution. We're going to do something kind of like importance sampling. So we're going to generate multiple hypotheses and then reweigh them. And that reweighing needs to somehow look at each sample and say, does it fit the data? And for that, we need this likelihood. And for now, we're going to convert our natural language to Python. We're going to generate code because the data might be formal, might be like a data structure, and the natural language is informal. So to bridge formal and informal, we need to lower things to Python. So that means that effectively our likelihood function gets to look at the data and can filter out bad proposals. So we might start with the data here. We're going to pass it to our bottom-up proposer. It's going to generate multiple hypotheses, think between 10 and 100. And then we're going to compare them to the data and see if they actually work. OK, so we took this model and we applied it to some basic concept learning problems. So these were things you could easily describe in logic. So things like a bachelor is male and not married. So imagine learning bachelor from examples. But also first order concepts. So a valedictorian is something which involves quantifiers. You got to sort of compare all the students within a school and say, for all students, why, if they're in the same school, then like the valedictorian's GPA is higher. So we took this task and data from this paper from Stipe and Edozi. And to get some intuition about it, subjects saw a stream of examples of some concept. They'd be told none of these belong to the concept. They would get these examples. They'd be told that's in the concept. Then they would see this, and they'd think, well, OK, I saw a green triangle. Maybe the concept is green triangles. So it's an online learning setup. And we're going to play it right now so you can get a feeling for what it's like. So here would be a batch of examples. You'd be told, these ones belong to the concepts. So think for a second, generate possible hypotheses. You would then get these examples. And we're going to just go through here, and when you think it belongs to the concept, hum. And the volume of humming will be like a signal of, on average, what humans think. All right, so think. Ready? Hum. All right. High entropy posterior. So those belong to the concept. Think for a second. We'll do it again. All right, so still some entropy. So typically after 2 or 3 examples, people get this. We ran this on people. 2 or 3 is kind of the magic number. Who knows what the concept is?
Same color.
Triangles, big squares, big circles.
It's kind of the most common color, the majority color.
Oh my God, I'm nowhere near.
All right, so sorry. It often works. In our subjects, it worked. They were paid, so you got to incentivize people.
There's some things you shouldn't say out loud. Just as a professional advice.
I'm using on the shapes, not the colors.
All right. Anyway, so here's our model. We have like language and code. We're gonna still be Bayesian, but we're kind of Bayesian over language. And so we have the neural network that is generating the hypotheses. So one thing that's sort of fun about this model is it can capture some kind of garden pathing effects in the human learners. So here they're trying to learn over successive trials. The ticks to limit trials, they do pretty good, and they all fail at once. And what's going on is that the hidden logical rule is that it has to be blue and also the biggest thing, And that's sort of weird to say. It might be easier to say, it's the biggest blue thing. And to kind of explain this failure, if we look at what the model is concentrating its probability mass on, it's saying it's the largest blue object in the example, or the biggest blue thing, which is close, a little bit easier to say than the ground truth. Yes?
What does the model get? Does it get pictures or
It gets text. It's not really seeing the images like you. So it's saying like, blue circle.
Okay.
So overall, it's a reasonably good fit, but it's not perfect. But what I think is interesting is that it's trying to get at this kind of compute-efficient inference. So our proxy for compute is how many hypotheses do you generate. Y-axis is fit to human data. You need somewhere around like 1,500 before it starts to be a reasonably good fit. So you don't need to like run your sampler but over like millions and millions of hypotheses. And that's driven by the kind of bottom-up process of you do top-down proposals. So you sort of close your eyes and ask the language model, imagine 100 hypotheses. You don't explain the data. So we also want to be flexible, both efficient and flexible. So to do that, we ran some new subjects on the concept that you saw earlier. Again, we paid the money and rewarded them, so they did better. But they, learned it. The model also learned it. It wasn't quite as good as the people were always, but basically, it's still learning it. And if instead you use a kind of conventional symbolic program synthesizer with a domain-specific language that is designed for the original data set, then interestingly, it doesn't fit this. And the reason is because in hand designing for the original data set, they accidentally left out some concepts, like the ability to count the size of a set. And therefore, because they didn't have the flexibility of natural language, it didn't fit as well. So in some sense, if you're on kind of the side of these like hand-designed symbolic representations, you would say, well, now I just amend my representation. I just add another patch. And you play this game a lot, but in practice, you just get a lot for free by going to language in Python. So in terms of the cursive functionality, what's really happening is we're being able to index this infinite concept space and project it down to a manageable subset. That's the bottom of proposals. And we're able to learn a kind of good inductive bias using a neural network. So the next thing we did is we thought about how to add active learning. So instead of passively receiving data, you do experiments. And so this is our new pipeline. So in everyday thinking, there's examples of this, like when we learn to use a new device, web page, or tools, when we sort of debug our printer, these kinds of things. That's kind of where we're experimenting with it, figuring out what's the problem. There's also analogs in development, like exploratory play, or when kids are learning how to see, they sort of selectively attend to good source of information. And we're really going to need probability here. We don't want just a single point estimate, not just one program. We want multiple hypotheses, because if I just tell you, hey, I think the answer is hypothesis H, that doesn't tell you what to do next. It's a lot better if you have multiple hypotheses, like this, a posterior, because then you might do an experiment like this, which kind of splits one of the hypotheses off, or like this. But you also want probabilities in order to say, well, I don't really believe H3 to begin with. Therefore, this is a great experiment because it splits H1 and H2. We also want to do online inference. So instead of sampling a big batch of things, we want to make incremental changes to our beliefs because we're interleaving experimentation and learning. So instead of this, it should look like this. And so we built a very similar model, except that our inference, instead of being like importance sampling, is more like a particle filter or sequential Monte Carlo. So using bottom-up LLM proposals. And we're going to do the experiments that maximize information gain. We do other things like consider kind of fuzzy, noisy hypotheses, which is important because your particle filter shouldn't kill stuff that's like kind of right. But this is basically the overall model. We looked at these kind of Blicket detector experiments. We were trying to learn a binary rule about what will turn on a machine. So this is a Blicket machine. It makes noise when it has some combination of things on it. You could see this in conjecture like, well, maybe at least one of them has to be yellow for it to activate. You might do some experiments where you get rid of all the yellows, and you would say, oh, it still activates. So then you would keep on alternating between forming hypotheses and doing experiments. And we're doing this mostly because of a long history of Blicket-style experiments in developmental psychology, where they have kids play with these things and figure out rules. There's also Blickets for grown-ups called Zendo, which is a board game that's really fun for program synthesis people. It's basically a Blicket experiment. Here's what it looks like. Here is an experiment done by Neil Bramley that we take the data from, where they had this interface for kind of Zendo. So what we found is that if you just point GPT-4 at this problem, it's kind of React style. It's not human level. The model I'm presenting is approximately human level. And interestingly, you can surpass human level by saying that the rules are hard and deterministic instead of fuzzy. So humans are a better fit with fuzzy rules, probably because we think more naturally in probabilistic ways, but the ground truth is hard rules. And this online inference seems to help here. So one other thing that we saw maybe a hint of is that we have this kind of compute budget in the model, which is how many samples we draw in order to update our hypotheses. And we tried both a small, medium, and large compute budget. And what fit the human data best was this kind of medium compute budget. So it suggests that maybe there's something here that's more of a process level account, like it's getting at kind of the underlying computations as people think through these problems. So a couple lessons here. One is, I really want to kind of advocate probability for thinking about these sorts of tasks if we want to be human-like. It's really, I think, essential for picking good experiments. And doing online inference was both more effective and more human-like. And we're going to take this insight with us into what is going to be in the second part. So before we start talking about the more engineering part of the talk, I want to reflect on why these models were human-like. So in my opinion, it's because they're approximating rational inference, just like evolution sculpted us to be mostly rational on average, over things that are expressive and flexible, like language and Python. It's not, in my view, because of LLMs. It's not like the LLM magically confers human-like behavior. All they're, quote-unquote, just doing is projecting down this incredibly rich space to a manageable subset and making tractable computations that would otherwise be incredibly unwieldy. So in part two, we're going to take these general ideas and apply them to other synthesis domains. So first off, to motivate this, imagine that you're trying to do synthesis of graphics. So here's a picture. Here's some code that draws it. And GPT-4 is hopeless. It doesn't understand how to link this image to this code. It's probably never seen this kind of code before exactly in this format. It's not like it's pre-training or fine-tuning data at all in really any sense. But nonetheless, you might have some unusual use case. And you want to do the same kind of thing I was showing you earlier where the LLM proposes programs and then you filter them. So the obvious thing to do is to maybe try and fine-tune. So you build some kind of data sets that says, when you see this image, write this code. But that's a hard data set to build. you got to think of a lot of graphics programs. You got to think about like your graphics language you care about. It's probably different from someone else's. If you work at Pixar versus Adobe. And they got to be like realistic natural graphics programs. So one popular idea, you see it in things like self-instruct and like wizard coder all over the place, is to make a synthetic data set and fine-tune on that. So here's what that looks like. We start with some human-written code, and critically, it's like 10 programs. It's not like 10 million programs. So 10 examples of the kind of graphic code you care about. You pass it to an LLM, and it generates a kind of remix of what you gave it. So it doesn't understand the program semantics, but it knows program syntax, and it can pattern match on syntax. So it will kind of autocomplete by recombining aspects of all the programs you gave it. The LLM does not understand program execution, but you can run the code with a program interpreter, and interpreters do understand execution. So you can get a valid program output. Yes?
So does it give that comment as well?
Yes.
Yeah.
Yeah.
But that's not correct, right?
Yes, good point. So the LLM does not understand program semantics. It generates reasonable code and comments that often don't really describe what the code is doing.
Yeah.
So we run the code. It makes stuff like this. And what's important is that, as you're saying, this comment is total nonsense. But this picture paired with this code, that is correct. That is correct by construction. And so you can run this many times. You get lots of images. And this gives you a data set of programs paired with the images that they produce. Yes?
But this may not be the natural distribution of tasks that you care about.
Great question. In 4 minutes, we will get to that. But that's fantastic. So that's the big problem with this, which is that there might be distribution mismatch. OK, so to address that, we're going to do what's sometimes called a wake-sleep algorithm. So to motivate this, we're going to run another Bayes net, where our hidden variable is going to generate our observed variable. And what we were doing earlier, the synthetic data generator, is we were kind of running this model forward. In what's sometimes called wake-sleep, there's another model that goes backwards. It's our inference network. And we're going to fine-tune it on the results of this synthetic data gen. In wake-sleep, though, these two models cooperate. They train each other. So the generative path is making data for the inference network. And as we'll see in a second, the inference network is going to be updated, or the generative path is going to be updated based on what the inference network does. And this will address exactly what you're just asking about. So we call this wake-sleep fine-tuning, and here's how it works. So you start with your prior over code. And this is some prompt with human-written code, but it doesn't really describe the distribution that you care about, because maybe you wrote it in like 10 minutes, or it's based on just like a very small prompt. But you can still generate synthetic data. In wake-sleep, we would call this streams. We would then train our inference network. And then during what's called waking, we would deploy this on real problems. This means that we have real examples of actual things that we had to program and real programs that solve them. So we can close the loop and then update our prior by adding that to our prompt. And then this becomes a cycle which kind of solves more problems and also develops an inference network that is better attuned to the true distribution of problems. So when you run this, what you see is that after the first sleep phase, you often don't solve a lot of problems. But you're able to solve some of them, meaning that on the next iteration, you have a better prompt from which to learn from. So here in particular, we had a bad initial prior. It told the agent, the system, that you only have to deal with short programs, but the real world had long, complicated programs. But it was still able to solve a few hard problems. So then during a second sleep phase, after fine-tuning, it's much better at the problems it really cares about. So here the x-axis is kind of number of steps during waking. It's the number of samples or search steps we've taken. And y-axis is number of problems we solved. So the reason why we're doing this, instead of kind of basic self-instruct, is that we might not know what kind of programs we care about. We want to just kind of preload our system with a good guess, have it go out into the world, and discover for itself what problems are valuable to solve. There's also connections to biological learning. Just to kind of situate this in reference to Tom Griffith's talk earlier, who was talking about how you could learn to be Bayesian. The kind of meta-learning stuff that Tom was talking about is about learning to be Bayesian through evolution. And this is more about learning to be Bayesian over more like the time scale of your lifetime, where it's not a few-shot learning problem, but it's also not like a million examples. You might have like 20 or 30 examples. But it turns out that in-context learning really only needs 20 or 30 examples. And that's fundamentally why this works. So we applied this to a variety of different domains, kind of flash flow style problems, functional programming style problems, and these graphics problems. We found it was actually just works better than we thought it would. So it was pretty good at these kind of list algorithms, really good at these like graphics programs. It was really graphics where it did the best. So then we thought, well, there's this popular data set out, the abstraction and reasoning corpus, and that's kind of like algorithms on visual input. So then we tried to apply it to that, and it didn't quite work. And at the end of the talk, I'll explain what was going on and why. OK, so before we get to that, though, I want to segue from talking about programs that describe the structure of an image to what I think is a good long-term goal that we haven't achieved yet, but we're trying to get there. We want programs that describe more like how the world works. So imagine an agent that's kind of trying to program itself and write its own code that says, here's the dynamics of the world. I'm going to use this understanding of the dynamics of the world to solve problems. So to motivate this, picture yourself as a robot hungry for apples, and you don't understand, your own ability to jump over ravines that have juicy apples at the top. So you make mistakes, right? Sometimes you jump and fall into the ravine. What we would really like is for our robot to have a model of how the world works, which says, here's how aerodynamics operate, here's how much I weigh, here's how much I can jump. So then you could imagine different outcomes, kind of mentally simulate the future, and then pick a good course of action. So these things are sometimes called world models. They allow a lot more than just predicting the future. It's also about imagining the past, imagining stuff right now that maybe you don't see, but you can infer. It's also not just reasoning about how your actions affect the world, but also reasoning about like what other people might do. So it's a lot richer than just this. But we're going to use this as a motivating use case of what a world model should allow you to do. And in robotics, there's kind of two ways that people often think about this. One is you train a big neural network that is like a world simulator, and that's one kind of world model. The other is that your world model is like in a planning language, like PDDL, and you kind of have it hard-coded into your robot brain. And what we want to do is start with something kind of like a planning language or some other sort of robot reasoning about how your actions affect the world language. But instead of hard-coding it, have the robot look at the world, try stuff, do the same active experimentation that you saw on Blickets and on Zendo, but in the real world, and then build a world model. So in the first version of this, we kind of tested like a null hypothesis. Like here's the most basic way of doing this. So we can think of a world model as something that takes a state and an action, and then says, here's the new state you're going to get, and here's the reward you're going to get. And this works for really simple video games. So like this Sokoban game where you're this green axolotl, and you're trying to push around this box onto the red targets. You get points whenever you do that. And mostly people like Sokoban because it involves reasoning over long timescales. So just training like a neural network policy doesn't work very well. But if you have a world model of the game, then it's much easier to plan over long horizons. And it maybe shouldn't be that surprising, but you can represent this game in a small amount of Python. And it also should not be very surprising to you that language models can do this, because Sokoban's a popular game, and its source code is on the internet. So you can prompt a language model with some Sokoban traces. It quickly figures out, oh, I'm playing Sokoban, and it writes the source code. It makes a few mistakes, but it can correct those. So to kind of make sure that it wasn't memorizing Sokoban, we tried sort of making changes to the game, and it seemed to not be quite as good, but it's still able to figure out how to write this code. But just to explain the kind of architecture we're using, it's very similar to a system called EMPA by Pedro Tsivitas. So there's some kind of code. It describes your world model. It's interacting with the world. The world tells you the state and what reward you're getting. We act by planning. And if it was just this picture, then this would be a hard-coded world model. But we want to learn the world model. So we're going to pass our observations to an LLM, which can be doing these online updates of our code, kind of similar to the Blickett experiment earlier. We were doing online updates of our beliefs about what activates a Blickett machine. Here we just have a more complicated Blickett machine. So I was hoping that because program synthesis is so data efficient, this would mean that our agent was also data efficient. So my grad student Hao Tang and I, we programmed this, and we plopped our agent into this grid world where it had the goal of opening the door. And this seemed like a very easy problem, and it should figure it out quickly. Instead, it took thousands of examples to learn how to open the door. So this was discouraging, but then we thought a bit more, and we realized that this is because we're only going to learn how the world works if we have good examples that demonstrate the dynamics of the world. So we need some good data, meaning that we need some kind of bias toward exploration. And there's many ways of doing this in reinforcement learning, but one that was kind of interesting from a program synthesis perspective is this kind of bias toward optimistic world models. So when you have multiple world models, you should prefer one, all else being equal, that predicts that you can achieve reward. This means effectively, the world model hallucinates different rewards, and even if those are wrong, it at least gets you kind of moving and trying new things. And as a consequence, when you add this optimism bias, you learn from far fewer examples. So that was a lesson for us. Instead of just favoring simplicity, we also want to favor some optimism in our world models.
Question?
Yes.
There's a pretty big literature explaining what are called the biases in human reasoning. There's a huge number of these things. Optimism bias being one of them. And some of them have been partly explained in terms of that humans have to have competition heuristics and or Bayesian reasoning. Has this been run against those human data?
No, it hasn't. So I do think there's a really interesting connection between optimism and Bayesian framings. Like if your posterior is broad enough, then it will capture some low probability models which predict that there might be some reward over there. Here, actually, we dropped the Bayesian framing. And I think that we would get some of this optimism for free if we were more Bayesian. OK, so that was kind of the null hypothesis. And it worked for really simple grid worlds. But that was honestly about all that it worked for. And when we thought a bit more, we realized, well, maybe we can't model everything in the rich world as a simple piece of Python code. But maybe we could model certain abstract properties of the world in Python. So to understand what this isn't, I want to explain, what people are doing in deep learning with world models. So one example of this that I love is a system called Genie. It got best paper at ICML, and it's wonderful. You can create a whole simulated pixel-level model of a virtual world, and you can actually play inside of it. At the same time, there's a bunch of stuff that we know about the world that is not captured by something that is operating at the level of pixels. So I know things that going to college helps you get a good job, that balance beams can tell if masses are equal, that high prices lower demand, that trees can live a long time. There's a bunch of stuff that I think is part of human-like world knowledge that is just going to be really hard to absorb for these pixel learners. So we're going to focus on a simple example here of thinking about balance beams. And we're going to work with the simulated robots, which is operating a balance beam machine. And it gets reward if it can balance the beams. So the same amount of mass on either side. And when it's done, it presses a button. It says, like, I got the machine to work. So there's different levels of abstraction at which you could operate. And we want to kind of go beyond the raw pixels We want to think, okay, there's some abstract property of some object being on top of something else. That allows us to think about how much stuff is on each platter in the beam. And then we can answer questions like, is the beam balanced? So if we have some trajectory like this, we're going to see the pixels, we want to abstract them into some higher level propositions. Here, we're writing them in this kind of first order logic-ish notation. So things like, is my gripper open? Is something directly on top of something else? And we're going to try and synthesize these state abstractions, which say that some abstract property of the world, and I'm going to reason about that abstract property and how it evolves over time. So one property is whether the mass is distributed evenly on either side of the balance beam. And it's not enough to just have this property. I need to know, how do these properties evolve over time? So like if I press a button, then as long as that property is true, then something about my state changes. And so now we have two kinds of programs, the state abstractions, and then programs that tell you how those state abstractions change over time. And you can do this with other things, like making coffee. So you have different abstractions, like is the coffee jug inside of the coffee machine? And for judging whether the coffee jug is inside the machine, you probably need to delegate that to something that understands vision, that can look at the picture and say, okay, when I'm looking at the coffee machine, is the jug inside? And so for that, we're kind of borrowing from Viper GPT and are having programs that call vision language models. So it builds a little query and says, okay, is the jug inside the machine? And then just like before, we learn these kind of dynamics for the abstract state. So that's the intuition. And you can think of it as building on top of the work we did earlier, the kind of null hypothesis, which was like this, where we had just one program. And now we're adding a second program, which builds a state abstraction. And we're learning, given this abstract representation of how the world is, how does our representation evolve over time? Sorry, what?
Is that an automated process?
Yes. So these are all automated. Yeah. So the supervision for the system is you put it into an environment, so you give it a reward signal. And one big assumption we're making is that we have pre-trained options or skills, things like pick and place and poke. So we can poke a button, and that's like one action. So we're not planning at the level of muscle movements. We're planning at the level of these abstract actions. Okay.
Sorry. Instead of doing that with this, you do it with something like chess. You expect concepts like concepts we know tables, or what happens if we do it in domain where you understand the structure?
So I'm sure it would work for chess because the LLM understands the rules of chess. And they're pretty good at kind of recognizing when they're seeing something they already know. I'm not sure how well it would work for things that are really out of sample. And I think part of what's going on is it knows about coffee machines and knows kind of how they typically work. So it can start to generate possible coffee machine code and then correct it if it's slightly wrong. For the balance beam, interestingly, as you saw earlier, it doesn't look like a balance beam, right? Yishao Liang, the student who led this, he kind of mocked this up in like a day. But the VLM was able to kind of think about like what's going on and like why is it turning on sometimes not, and say like, oh, it didn't use the word balance beam, but it said, oh, when they're distributed evenly, and it was able to write code that kind of captured that logic. Okay, so this is our picture. We're synthesizing two programs. Big caveats, we have these kind of pre-trained options or skills. So just to kind of situate this more with respect to these kind of Gen AI world models, here we're deliberately trying to construct an incomplete model of the world. As a consequence, though, we're going to be able to learn it from relatively small amounts of data, assuming we have good pre-training. So pre-training that tells us not just about code, but how code relates to stuff in the world. We have a variety of other limitations that I think are not intrinsic to the approach, but just were in this particular paper. So here we're assuming that everything is deterministic, fully observable. We have a fixed inventory of skills. We don't learn new skills over time. I think that those restrictions, though, can in principle be relaxed. One thing I want to highlight that I thought was interesting about this, though, is that it builds these abstractions hierarchically. So to explain that and why that comes out naturally from code, if we start from kind of our pixel level observation, we can imagine basic abstractions, like is one object directly on top of another? And that would work by querying a vision language model. Once we have that, though, that becomes a function we can call later. So we can build other state abstractions like, is some object on top of a plate? So the vision language model thought these things look like plates, so it called them plates. And then that allows us to define another abstraction, which says, are things distributed evenly across the two plates? So just to mention one cool thing and one not cool thing. So the cool thing, on plate is recursive. So it's only recursive abstractions. The not cool thing, we didn't actually learn directly on. We hard-coded that because it just seemed like a really important primitive. So we have that disclaimer. But it did learn the rest of the hierarchy.
Just a quick question.
Yes.
These things produce infinite loops.
Sorry, what?
They sometimes produce, like you mentioned, the recursive.
Yeah.
Can they intrinsically not finish or something, the program?
Yes, you always have timeouts.
So you have to time it out?
You always time out this.
Okay, gotcha.
Okay, so a couple lessons. One, it was really tough to model the whole world in code. Like the null hypothesis, I think, kind of doesn't exactly work, or at least it's very tricky to get working. We're just learning this projection of the world and the reason about the dynamics of that projection. But when you do this, it becomes easy to build symbolic hierarchies. Okay, so in the last part of this talk, we're going to think about how much we can and should model in code and what the limits might be. And to do that, we're not going to think about world models. We're just going to think about kind of these abstracted function learning problems, which are nonetheless really diverse and interesting. So in particular, we looked at these problems from the abstraction and reasoning corpus, which if you haven't seen them, are these kind of grid input-output problems. This might be an example input grid. And then you'd be told that the target output grid is this. So I think it's kind of like bouncing, almost. You would get like a couple more examples. You're trying to generalize from only 2 or 3 examples. And then you'd have to draw the output grid here. So to do this, you need good priors. You also need to be highly flexible. You need to be able to write some pretty non-trivial code, actually, to solve a lot of these ARC challenges. So here's a few other things you see in ARC, things like pathfinding mazes, a lot of kind of objectness ideas, like contact between objects. There can be almost like a 3D aspect to them, where one object is in front of another. It's very diverse. So the way that we would solve this, using the stuff that we talked about earlier, is you would have your training inputs and outputs, and you want to predict your test output for your test inputs. And you would do this by doing program induction. You conjecture some hypothesis, a function, f, and then you would execute that on the test inputs to make your prediction. I'm going to call this pathway induction. When you draw this picture, it becomes clear there's another pathway, which is what I'm going to call transduction, which is where you form your prediction by making direct comparisons with the training examples. So there's no intermediate function. So think of things like kernel methods or like transformers as they attend back to the earlier examples. Whenever you just shove something into a neural network and say, give me the answer, I don't care about the internal symbolic code. So what we did is we compared neural networks for induction and transduction. So we're going to learn neural nets to either make code or just make predictions. And we're going to test these things on ARC. So to do that, we made this big data set, a big meta-learning data set of ARC-style problems, which said, here's some input grids, here's some Python code that maps the input grids to the output grids. And we assembled about 400,000 synthetic ARC-style problems. All of them are solvable with Python. So we're never going to train our system on anything that cannot be solved in code. So here's examples of the kind of synthetic ARC-style problems. They're generally not quite as interesting as real ARCs, but they're pretty close. So now we have this kind of contest between these two approaches. That was produced using kind of the prompting method where you show it examples of ARC programs and then ask it to make more ARC. Exactly, same kind of approach. All right, so we have this kind of contest between program synthesis and in-context learning effectively, like having a transformer just do it. And I was rooting for program synthesis, and the results were really weird. It was a tie. I didn't expect that. So then I thought, well, that must be because there's easy problems and hard problems. And they both solve the easy ones, and they're both not solving the hard ones. So then we made a Venn diagram of what each of them solve, and that's not what's going on. So this is very strange because they were trained on the same problems. Every single problem they ever saw was solvable with a program. And they were both fine-tuned from the same base llama model. So this is not accounted for by some difference in pre-training. So then we thought, well, why don't we just do both at the same time? If they're both good, but they do different things. So we made one data set, trained two models, and ensembled them. And interestingly, this actually does surprisingly well on ARC and is kind of close to human level, like slightly worse than the average human, but it's kind of in the ballpark. So what we learned from this were a couple things. So one is that these two styles of either generating symbolic hypotheses or imitating symbolic hypotheses, so induction and transduction, they seem to be complementary even when we controlled for a variety of different ingredients. So this is kind of a speculation, but I've often been a little bit skeptical actually of the system 1, system 2 divide. It seems a little bit simplistic, but this does seem to kind of go in that direction. So just,
Question?
yeah.
Yeah, can you go back a slide? One more. Going back to the, yes. So here's a suggestion. Take your data set, train up both the induction and the transduction on a divide in two, held in, held out. Train both of them on the held in. But then don't simply use the held out to choose among them. Use the held out to actually figure out under what conditions which one is better, and then go with that. Now train on everything and use that. I can almost guarantee that that will do better than this.
Interesting. So we could try that. And I do think that it is actually easy to tell for a problem which one is going to solve it. Like you can kind of get a sense for that. Yeah. But with induction, there's an interesting property, which is you get to do generate and test. So if you go back to this picture, you get to generate multiple hypotheses and then check them. So that means that when we're ensembling, we actually just run induction for up to some compute budgets. And then if nothing works, we go to our backup plan. So we kind of are able to sidestep this problem of deciding what to do because we kind of have a primary method and then a backup. Yes?
So how do you know whether something works or not? Because you test it on the...
Right, so we tested on the training examples.
And can you also liken this induction to chain of thought reasoning?
In some ways, yeah. I mean, it's a kind of like intermediate symbolic steps. I think the difference is that with chain of thought, you can't verify correctness. With program generation, you get to run the code and check it against the data. And that's the key reason why when we're ensembling them, there's, we don't have to really decide which one to do. We just try the thing that's checkable. And if it fails the checks, we go with the thing that we don't check. Yes?
Can you tell us a little bit more about the transduction step? Is it a large language model that you fine-tune?
Yeah.
Is it a transformer that you train from scratch?
So these are both Llama 3.18b. So it's an 8 billion parameter model, pretty big, not enormous, but like pretty big.
And it's fine-tuned?
It's fine-tuned, yeah. All right, so that's actually it. I just want to plug some students and collaborators. So the student who led so these two students led the ARC stuff. One of them's on the job market. One of them is on the PhD markets. Wending also did the programming by examples, kind of graphics stuff. This ARC stuff is also a collaboration with Zenit Tavares' group at Basis. And we're trying to maybe hire some people jointly to push more in these directions. So that's it. I'll take questions.